Let's talk about polar coordinates. So polar coordinates are a different way to express the location of a point in 2D space. So it turns out this whole time up until today, we've been using what's called Cartesian coordinates. So that's the fancy name for a point labeled x comma y. For example, if we say the xy point is 2 comma 3, what we're saying is in the xy plane, we're going to go over 2, up 3, and that puts us in exactly this location in the 2D plane. So polar coordinates represent a point still as parentheses number comma number, but when you specifically state that you're in polar coordinates, those numbers are not x and y, they are referred to as r and theta. So this is still going to refer to a point in the 2D plane. So we can see this as still x and y axes, but we're using them differently now. So if we have a point right here, and we say this point is r comma theta, r represents the distance from this point to the origin. So r is whatever that distance is right there. And then theta is the angle of rotation off of the positive x-axis, the same way that thetas work in the unit circle for trig. It'll represent the angle that brings that radius up to the point. That amount of information is still enough to get you to any location in the xy plane. For what it's worth, when we say polar coordinates, the pole has to be defined. So the pole is supposed to be like the one central location, which would be 0, 0. So the location of the pole here, its xy coordinates are 0, 0, and its r theta coordinates are also 0, 0. So that's the pole in polar. All right, so let's see some examples here. Let's say you have an r comma theta point that is 1 comma pi over 4. We're going to see a lot of pi in these next few sections because this theta is an angle. So we're going to see angles in radians, of course, always radians. We're going to see angles in this spot here. So to plot this point, we're going to the xy plane. All right, so I'm going to consider the theta value first. This is the angle pi over 4. So I'm going to be somewhere exactly halfway through this first quadrant. Now, exactly the distance along this radius I'm going to travel is 1. So mark a point where that distance is 1, and my point will be right here. Right, so to drive home the point, this is still the xy plane. It's just that we're identifying this point differently. I'll label that this angle is pi over 4. And if you think about it, if this little radius here is 1, this point is secretly lying on the edge of the unit circle. And if its angle is pi over 4, we can actually tell that its xy coordinates are the cosine and sine of pi over 4, respectively. So r theta being 1 and pi over 4 corresponds to x and y both being root 2 over 2. Let's try one more. Let's say your r comma theta point is 2 pi. Okay, so again, I'm going to consider the angle first, even though it's listed second. So having an angle of pi brings me all the way over here to the negative x-axis. And if my radius out from the origin in that direction is 2, that puts me right here. The xy coordinates of that point would be negative 2 comma 0. I also want to use this as an example to point out that unlike Cartesian coordinates, a point's representation in polar coordinates is not unique. So polar coordinates for a point are not unique. And what we mean by that is that you can have this one single point, this one location in the 2D plane, and there's lots of different r theta combinations that could refer to this same position. So for example, I could have said that the r comma theta point is 2 comma 3 pi. So if I loop around 3 pi, I go 1 pi, 2 pi, 3 pi, and then I go out 2, and I'm in exactly the same spot. We can even have a negative radius number, just like we can have negative angles. So we could have a radius of -2 and have the angle be 0 or even 2 pi. So having an angle of 0 or 2 pi puts me on the positive x-axis. And then the radius being -2 means instead of going out in this direction, +2, we're going to go backwards 2. So all of these land in this same position. We're going to have a lot of different tasks that we're concerned with when we're doing stuff with polar coordinates. The first task we'll worry about here is converting a point either from Cartesian coordinates to polar or vice versa. All right, so conversion of coordinates, we'll start with polar into Cartesian. So in the examples above, we did see a couple of times where if it happens to be in a very convenient location, you can just kind of come up with the XY coordinates of a point given in polar. But in general, we need a strategy that's always going to work, even if the numbers aren't particularly nice. So we're going to consider if we are in, I'll put my little picture over here. If we're in polar coordinates here, we have a point, and we know that the distance from this point to the origin, we're going to call r. And then if we drop a perpendicular line straight down to the x-axis, oops, sorry, that's not x, that's y, and then this line right here is x. So we have this horizontal distance is the x value of that point. This vertical distance is the y value of that point. So if we did, for example, the SO of SOHCAHTOA for this triangle, noticing that this angle is theta, that would mean that the sine of theta is opposite over hypotenuse. And this gives us, of course, that r sine theta equals y. If we do CA, we would get a similar statement, but with x and cosine. And that leads us to the two important equations here. So the x value of the point would be r times cosine theta. The y value is r times sine of theta. And this is true even if the radius r was negative. These formulas still work and kind of takes care of itself. For example, let's say your r comma theta coordinates are -2 pi over 4, just to see this work out with a negative radius. And we want to turn this into its x comma y coordinates. We would say, okay, well, x equals r cosine theta. So that's -2 cosine pi over 4, which is -2 times √2 over 2, which simplifies to -√2. And then the y value of the point is -2 sine of pi over 4, which simplifies the exact same way. We get -√2. So the xy point that puts you in exactly the same location here is -√2 comma -√2. Converting in the other direction is a little bit trickier. So this will be the conversion from Cartesian into polar. Cartesian into polar. Right, so we can again kind of play with this triangle. If we do TOA in this triangle here, what we end up with is tan theta equals y over x. So that can help us sort of backtrack what theta must have been. And then we could also do the Pythagorean theorem here, and we get that x squared plus y squared equals r squared. And again, we can use that to potentially backtrack for the value of r. Right, so let's see an example so we can figure out exactly why this is so tricky. So let's say that your XY coordinates are exactly from the previous example. So negative root 2, comma, negative root 2. How could we backtrack to get back to what this R theta combination would be? I also want you to keep in mind that there's not uniqueness here. So there's potentially a bunch of different correct answers. As long as it's an R and theta combination that give you this same location, it's a correct answer. Okay, so let's do x squared plus y squared equals r squared first. That would mean that the r squared is negative root 2 squared plus negative root 2 squared. And that gives me 2 plus 2. Yeah, 2 plus 2 is 4. Okay, so then r is either 2 or negative 2, depending on how you pick your theta. Okay, so we're going to leave this here and do the tan theta. So tan theta is y over x, the y value of the point over the x value of the point, which gives us exactly 1 here. So theta is an angle whose tangent is 1. The first angle that comes to mind that has this property for me is pi over 4. So I'm going to say, all right, let's pick theta equals pi over 4. I could pick a different angle here, and it may affect the rest of my solution. But again, remember, there's not a unique answer here, so we can have lots of correct answers. All right, so I have to come back here and pick an appropriate radius value. And it's all about the actual location of the original XY point, specifically what quadrant it is. I don't need a really nice graph of this, but you'll notice its X and Y values are both negative. So this point is somewhere over here in the third quadrant. So if my angle is pi over 4, I'm going to pick a radius of negative 2 that gets me in the correct direction. Instead, I could have picked an angle of 5 pi over 4 and then have a positive 2 radius, because then I would be heading in the right direction. Okay, so the way I have it, my r theta would be negative 2 comma pi over 4, which is in fact exactly how that point showed up the first time.